In this subsection, we're going to discuss a few more topics regarding confidence intervals. First, where does this t equal y bar minus mu divided by s divided by square root of n, where does this expression, or how does this expression have a t distribution for it? Well, there are some underlying assumptions that we have with this, if you remember, and that is y1 through yn need to be independent random variables representing our sample that we have, each with exactly the same normal probability distribution. Now, to see why this has a t distribution, let's consider the following situation. Suppose we have a random variable z. It has a standard normal distribution. And we also have a random variable w, which has a chi-squared distribution with new degrees of freedom. Also, let's assume z and w are independent random variables. With that, then, one can show that z divided by the square root of w divided by nu has a t distribution with new degrees of freedom. Okay, now, to get to this expression then for t, we're going to let z be y bar minus mu divided by sigma divided by square root of n. We've seen this expression before when we were talking about the central limit theorem, and we said that has an approximate standard normal distribution based upon the central limit theorem as long as our sample size is large enough. But if y1 through yn have normal distributions themselves, which of course then goes into making up y bar, then this z has an exact normal distribution with it. Also, we saw before, if we let w be n minus 1 times s squared divided by sigma squared, w has a chi-squared distribution with new degrees of freedom. So if we put all these components together here, just do a little bit of algebra, then what we can see is we get our expression for t. So it gives you a little bit of a background about how this t distribution comes about. Also note that one can actually show y bar and s squared are independent random variables. If you're interested in seeing an actual proof on that, you can take a look at Cassell and Berger's mathematical statistics textbook on that. So why do we make all these mathematical assumptions here? Well, whenever you do research, typically the way you first approach is that you make some assumptions. You try to make things as simple as possible. And you look to see, can one show in the simplest setting, does something work? And then if you can show it, then you try to generalize, generalize, and generalize, and generalize to see if the same result holds true. And essentially, that's somewhat like what's happened here. So while we have these underlying assumptions for t to have a t distribution, what statistical research has shown that t has an approximate distribution in many, many, many other cases. And this allows then this confidence interval to work as expected. We've kind of talked about that before in terms of what does expected mean. And what that says is if you were to go out and take a sample, calculate the confidence interval. Go out and take another sample, calculate the confidence interval. Suppose you do this a large number of times, maybe 1,000. Then 95% of those, if we were finding 95% confidence intervals, 95% of them, of those intervals, should contain the population mean that you're after for this interval. That's what expected means. Well, how can we actually see if this is true without actually us going out and taking the samples? Well, we can use a computer to do what's called Monte Carlo simulation to investigate it for us. And that's what we're going to talk about next. So back when we were talking about the central limit theorem, we talked about a particular example that dealt with this particular probability distribution, which is obviously not a normal distribution. And we showed that even with a sample size of 20, we take it 1,000 different times. That central limit theorem essentially works in terms of we have an approximate normal distribution. So what we're going to do is work in this same particular setting. Here's the PDF once again. And if you remember, in this particular setting, we have mu equal to 2.8571. And here's the actual data that we had simulated in the past. So the first row here was the first sample size 20. So y1, if our random variable is denoted by y, is 3.41. y2 is 2.79. And y20 is 3.59. This was our first sample. Next sample, y20 was 3.34. Next sample, y20 was 3.58, and so on. Let's now find 1,000 different confidence intervals. In other words, find a confidence interval for each of the samples. So we're going to find 95% confidence interval, so alpha is going to be 0.05. And similar to what we've done before, we're going to use the row means function to find the mean for each row of this matrix that has 1,000 rows of samples of the size of 20. Oops, let me do a head on that. So the first mean is, for the first sample is 2.96. The mean for the second sample is about 3.11, and so on. Now, there's another way that we could find all these means that uses a more general function in R. And that is, we can use the function apply, where I want to apply the mean function, that's what the fun argument is, to every row of set 1. And the margin equal 1 argument, and argument value corresponds to say I want to do it per row. Let me just restate that because I didn't say that very well. So what the apply function allows us to do is apply a particular function R to either rows or columns of a matrix. Where my matrix is set 1, I'm going to apply the mean function every time, and I want to do it by row. That's what margin equal 1 does. If I do margin equal 2, it does it by column. This will give you exactly the same means as we just saw. Now, the reason why I'm introducing you to this particular function, it's a very useful function, it's very general, is because it can work with other functions as well. So I could, for example, use the apply function, but now find the standard deviation for each row. In other words, find the standard deviation for each sample. So let me go ahead and do that. Do the head up function on it. So the standard deviation for sample number 1 is 0.7. For sample number 2 is 0.56, and so on. Then I got 1,000 means. I got 1,000 standard deviations. Using those, I can find 1,000 confidence intervals. So to find the lower limit for these confidence intervals, I'm going to take each of those means. So I got 1,000 of them. I'm going to subtract off from each of these the corresponding value that I need from the t distribution, multiply it by each of the standard deviations. So again, I get 1,000 of them there, and divide each of those by the square root of n. So notice how R works here. It finds the first mean, subtracts off that quantile from the t distribution, it gets the first standard deviation, multiplies it by that t value, and divides by the square root of n. Then it goes to the second mean and does exactly that same process. So this is how I find my lower bound. This is how I find all my upper bounds. I'm going to put them into a nice little data frame to display them. And so the very first confidence interval from that first sample is 2.63 to 3.29. And remember what mu was. Mu was 2.8571, and so the confidence interval did indeed capture that mu, or covered it, some people will say. For the second sample, 2.8571 is within the interval as well, so the interval captured mu, or covered it. Now for the third sample, notice we get a confidence interval of 2.94 to 3.48. So in this particular case, the confidence interval did not contain mu. So we like to be able to summarize that then over all 1,000 intervals. So similar to what we've done before, let's do like a logical comparison. I want to look at all the lower bounds. Is it less than mu? Because if it was, that says that mu is at least above that lower bound, so it has a chance of being in an interval. And so what's returned is we get some trues and falses. So for example, the 937th sample has mu actually less than, the 937th interval has mu less than that lower bound. So mu is not inside the interval. I could do exactly the same thing with the upper bound as well, but now I'm looking at, is the upper greater than mu? If it is, then great. If it's not, then we know that mu is not inside the interval. But what we actually want to check is both at the same time. Is mu greater than the lower bound? And is it less than the upper bound? If it is, mu is inside the interval. If it's not, the confidence interval does not capture that mu. And this is what we get. Now let's do some math with these trues and falses. So I want to find the proportion of the proportion of times I get a true. In other words, the proportion of time mu is in the interval. And we've kind of done this idea before. I'm going to use the main function with that. I'm going to put an object which I'm going to call coverage. Coverage is the term that we use in statistics to represent how often is the parameter that we're trying to estimate inside the confidence interval. In this case, 95.5%. So this confidence interval procedure here appears to work rather well. We are finding 95% confidence intervals every time, and for these 1,000 samples, we get it 95.5% of the time. If I were to go and take another set of 1,000 samples, it won't be exactly 95.5% probably. But what will happen, and you can try this on your own, is it should be somewhere close to 95%. So this is telling us that the confidence interval works, despite all these mathematical assumptions being violated. Okay, let's get back to the document here. Here's a plot of the first 50 of these intervals. So we looked at the first one, we looked at the second one, and notice how that third one, I should have mentioned this before, this red line is drawn at 2.8571, which is where mu is. This second interval, the third interval, does not contain mu. But we can see as we go across the entire plot that the confidence intervals generally do contain mu. And sorry, I didn't explain this plot very well to begin with, so let me just try this again. I apologize. So what we have on the x-axis is the particular interval number, meaning for sample 1, give me the interval. Sample 2, give me the interval, and so on. On the y-axis, we have the actual, let's say, GPAs, where the lower lines here represent the lower bounds. The upper lines here represent, the lower lines represent the lower bounds. The upper lines represent the upper bounds for these confidence intervals. These dots just represent, that would be y bar. You can see the code in the program for how this corresponding plotting function works. And so in this particular case, again, for the third interval, representing the third sample, we can see that the blue line, the blue upper line, the blue lower line is all above where the red line is, which is where mu is. So hopefully the second explanation works for you. If not, please ask. So what about other sample sizes? In my program itself, I have the code for using sample size of 30. And again, we get a coverage level that's close to what we would expect if this confidence interval is truly working, close to 95%. For a sample size of only 10, we get 94.1%. That's still pretty close to 95%. And if I were to keep on going all the way down to just a sample size of 5, I happen to get, for this particular set of 1,000 samples that I took again, 95% on the dot. So that's kind of cool. Now, one problem though, so you might be thinking, okay, well, why don't we just use a sample size of 5 instead? It's easier to take a sample of size 5 than 20 if we were to actually go out and take samples of GPAs and stuff. The problem corresponds to what we had discussed previously, and that is the confidence intervals will get wider for smaller sample sizes. Make sure you understand why. Here are two plots that help to demonstrate what's happening with these confidence intervals. So the top plot's for n equal 5, and the bottom plot's for n equal 20 using the exact same intervals that we had gotten previously. The key is with these two plots is that the y-axis scales are exactly the same. And so we can see with a sample size of only 20, with a sample size of 20, these intervals are much shorter in width than the ones with a sample size of only 5. Okay, so that just gives you a few additional topics then regarding these confidence intervals for mu.